here, and we talked about basic. Oh, come here. We talked about basic stoichiometry, um, and really your basic stoichiometry sort of steps are, as we talked about, you want to always make sure that you start with a balanced equation. Remember that obviously it does not work if you are not starting with a balanced equation. You then want to take whatever they give you and convert it to moles. You then want to use the mole to mole relationship from the equation. Remember, that is really just our coefficients. And you want to find, obviously, whatever they gave you and whatever you're trying to find are the two things you want to look at. And then usually in a basic stoichiometry problem, you will then be going from moles to some other unit. And again, a lot of times that is to grams, for example. And molar mass is again used very often there. And also up here, molar mass is oftentimes used. Now, again, as are really these four sort of steps, you just kind of follow them in order. Should lead you to the right answer. We also talked about limiting reagents. And with limiting reagents, we also have limiting, not limiting reagents, but excess reagents. And the limiting reagent is the one that gets used up first in the chemical reaction. The excess reagent is the one that you have plenty of. You'll still have some left over when it's all said and done and the reaction is over. And the reason it's important to determine, for example, your limiting reagent is once that limiting reagent is used up, you basically cannot make any more products. So what that means is it's always the limiting reagent that you should use in your calculations in terms of how much product you're going to produce. It is the one that will determine, again, that amount of product it is possible to be produced in this reaction. Um, how do you know you have a limiting reagent sort of situation? Well, you have basically one way to sort of really know it is if you are given enough information about all the reactants or both reactants, enough information that from that piece of information you have about the reactants, you could actually get to moles, then you know it's a limiting reagent problem. So if you have basically all the information about the reactants and enough information, whatever that information may be, but if you can directly just calculate moles from that information, it is a limiting reagent. We talked about two ways to handle limiting reagent problems, really three ways. One way is just to do it like we were doing basic stoichiometry problems. And again, around here, you'll do a calculation to determine the limiting reagent. And that calculation is just a simple stoichiometry calculation between the two reactants. And the goal there is to figure out, for example, you could choose either reactant, it doesn't matter. You could choose one reactant and try to figure out how much of the other reactant you would need to use up all the starting amount of that first reactant. And once you figure out how much you need of the second reagent, you could compare it to how much you have of that reagent. And if you have enough, that means that reagent is the excess reagent and the other guy would be the limiting. Or if you calculate and you compare to how much you need to how much you started with and you do not have enough, then that reagent would be your limiting reagent and the other one would be your excess. So the good news is you just got to figure out one of them and the other guy is the opposite sort of reagent. So that was one way we talked about it. We also talked about a very popular way people are taught to do it is just do two separate stoichiometry calculations, starting with one reactant going to the product and then take the other reactant going to the product. And whichever one produces the least amount of product is your limiting reagent and your theoretical yield. Third way, which is also a nice little way, is we talked about ice tables, and you could do an ice table approach where you get your starting moles of each thing. And you have your starting moles. You can just zero these guys out. This would be like a minus x, a minus 2x, plus x, and plus 2x. So remember, the change part is represented by x's. We do minuses here on our reactant side because it's decreasing with time. We do our pluses on the product side because it's increasing with time. And really, really important when you do the ice table sort of approach is we do take the coefficients with our x's. So if you do not take the coefficients with your x's, and obviously those that do not have a coefficient in front of it is just one, you will not have the right mole-to-mole relationship. So that's what using the coefficients does for you. Sort of the stoichiometry part of it, all kind of bundled together in this calculation. But it's really important on the change part that you take those coefficients and add them into the x's. Again, in this approach, what you would do, as we talked about, is basically just drop down here to our ending line. And what you would do at this point to figure out the limiting reagent is just set the two reactants equal to 0 and solve for x. And whichever x is the smallest when you do that will be your limiting reagent. And it will also be all the x's in the equilibrium line of the table. So once you find out for x, it'll be this x, this x. So that would be 2x if I copy that down right. It would be that x, and it would be that x as well. And again, like I said, kind of the benefit to this is you can really quickly answer pretty much a lot of questions that are asked in stoichiometry limiting reagents, like how much of each product you would produce. You could also figure out how much of that excess reagents left over as well. So without maybe having to start back up with a whole brand new sort of calculation to do so. So it's a really good method. In addition, it is sort of the calculation you'll use in 200B if you're planning on going to 200B. Calculation very similar to this calculation as well. Any questions on any of that there? All right, so why don't you give one a go here? I think we left off here. We got 124 grams of aluminum reacts with 601 grams of iron 3 oxide. How much aluminum oxide is produced? And some numbers here. I think aluminum 2698, iron 5585. I think. Then who else we got there? Oxygen. Oxygen 16. I think that's everybody. All right, so take some time there and calculate it up and see what you come up with. So let's take a look. So again, we talked about a few different ways to solve these type of problems, and again, no matter which way you kind of choose, kind of the first two steps are always the same. You want to make sure you have a balanced equation, which I kind of see some numbers there, so I'm going to hope that's balanced. The next thing you want to do is take whatever they give us and convert them to moles. In this particular case, we're given 124 grams of aluminum, and we're also given 601 grams of the iron 3 oxide. When I look at that, I see that I have grams of each reactant, and definitely from grams, I could directly get to moles of each reactant. So that is the key right there. I basically have moles of each reactant. And because of that, I could definitely get those moles, and that means that it is a limiting reagent problem. So just by knowing that, that's going to tell you it's a limiting reagent problem. And again, you got to do that sort of extra step. So first off here, I'm just going to convert everybody into moles. So we'll take our 124 grams of aluminum. We'll use the molar mass there of aluminum, which is 2698 we get from the periodic table. Going to put grams on the bottom so they cancel. 124 divided by 2698. Going to get us about, we'll call it 4.59, and we'll go 6 moles of aluminum. We're going to do the exact same thing for our other reactant. So we have 601 grams of iron 3 oxide here. We're going to use the molar mass from the periodic table of iron 3 oxide. So that is 2 times our 5585 for our iron, plus 3 times 16 for our oxygens. Going to get us 159.7 grams per mole from the periodic table as our molar mass here of our iron 3. Taking 601 and dividing it by 159.7, going to get me a 3.763. 3.763 moles of our iron 3 oxide. Any questions so far? Yeah.
There are two atoms of aluminum.
There is a reminder that when you calculate the molar mass, which I think is maybe what your question is, why I didn't incorporate the 2 in there, you don't do that. So molar mass is always per mole, regardless of what the coefficient is in the equation. That means you just simply take the formula for it. We only use really the coefficients for like stoichiometry type of calculation. So if you use it for the molar mass and stoichiometry, you're going to be in trouble and stuff like that. So molar mass always based on just the formula by itself. Yeah. Other questions? Okay, so this basically represents the starting amount, right, that we have of each of these reactants we're going to toss together and whatever we're tossing it together in. So I'm going to show you that first method we talked about, which is I'm going to figure out my limiting reagent. So in this case, I'm just going to pick one reagent. So I'm going to try to figure out how much iron 3 oxide I need is needed to use up all of the other reactant, which is the aluminum in this case. So basically, I'm just going to do a very simple calculation between the two reactants, taking my starting amount of aluminum and figuring out based on the equation how much of that iron 3 oxide I have to put in there to get rid of it all. So I'm going to take my 4.596 moles of aluminum. I am now going to do the mole-to-mole relationship between iron and aluminum and iron 3 oxide, and that is 2 moles of aluminum gives us 1 mole of the iron 3 oxide. So I'm going to use that here in this calculation. Opposites cancel, so the moles of aluminum go on the bottom and the mole of iron 3 oxide go on top. So this calculation between the two reactants is simply just to try to figure out which one of those is the limiting reagent. So we're going to go 4.596 divided by 2, and we will get 2.298 moles of iron 3 oxide is needed. So that number represents how much iron 3 oxide we would have to put in there to get rid of 100% of all the aluminum that's hanging out in there. Now, what I want to compare is I know I need 2.298 moles of iron 3 oxide. I want to compare with how much I have starting of that reagent. And I have 3.7 moles of it. Do I have enough? I do have enough, right? I only need 2.2. I got 3.7. So I do have enough. And because of that calculation, I now know that this guy is my excess reagent because I do have enough. And by default, that would mean in this case, the limiting reagent here is our aluminum. Any questions on that calculation there? And again, it's just simply to determine that fact. You could have done it the opposite way around, like we talked about before. You could have tried to figure out how much aluminum you needed to use up all the iron 3 oxide. And what you would find, you will not have enough. And it should give you the same answer in the end of which one's your limiting reagent and which one's your excess reagent. Any questions on that? Also, a really good example because many people, as I mentioned last time, will do a problem like this and go, well, I got 4.5 moles of aluminum and only 3.7 moles of iron 3 oxide. So it must be the iron 3 oxide is the limiting reagent, right? Because it's a smaller number. As I mentioned last time, not the case. You do have to kind of do it through a calculation here. And in this case, actually, the one with more moles to start with is actually the limiting reagent based on the stoichiometry of the equation. So you have to figure that part out through a calculation. It's just not like whichever one's the smallest number of moles when you're comparing your starting moles. All right, now that we figure that out, we basically could just get right back on this really wasn't step number 3, I guess. We could get onto our kind of 4 steps. We can now do our mole-to-mole relationship using the limiting reagent. So we'll go mole to mole. And in this case, because the aluminum is the limiting reagent, we're going to go from that guy now to our product, which is the aluminum oxide. And from the equation, it is 2 moles of aluminum for every 1 mole of aluminum oxide. So 2 moles of aluminum. It gives us 1 mole of aluminum oxide. So also really important is at this point, you do want to make sure you're going back to the starting amount of your limiting reagent and using that number. So we're going to go back to our starting amount here of our limiting reagent, which is this number here. We're now going to do our conversion to our products here. So again, 2 moles of aluminum gives us 1 mole of aluminum oxide. And we'll get an answer. I'm just going to do a step by step. Once again, as we talked about last time, you can do it at this point in sort of a big calculation if you like and continue on. But we'll end up with 2.298 moles of aluminum oxide. And we do want grams, so we will have to go back to the periodic table now and get the molar mass of aluminum oxide. So that is 2 times 2698 plus 3 times 16. Looks like 100 and, I don't know, we'll call it 102 maybe, if I did that right. 101.96, I'll go with it. Moles, grams per mole. And again, that comes from our periodic table. And we'll multiply that times our 2.298. And that's going to give us about 234 grams of aluminum oxide would be produced here. And this again would be known as our theoretical yield. Yeah. And obviously this is our 4th step there along the way. Any questions on that there? Now, as we also talked about, a very common question is how much of your excess reagent would be left over. And you could also calculate that, not by doing that. So if we wanted to know how much of our excess reagent was left over, in this particular case, we're actually lucky because we chose correctly. We don't necessarily have to go back and do another sort of calculation too much. We know that to use up all of our limiting reagent based on this calculation we did earlier, we would need 2.298 moles of that iron 3 oxide. So to figure out our leftover iron 3 oxide, that would be the moles of it that we started with, which was 3.763. Gonna subtract it from the moles that was needed to use it up, 2.298. And that will tell me that in terms of our iron 3 oxide, we would have about 1.465 moles left over. And we also could just use the molar mass of iron 3 oxide, which was 159.7 that we calculated earlier. And we can turn those moles into grams. And that'll get us about 200, believe it or not, 34 grams of the iron 3 oxide is left over, right? We started with about 601 grams. So we use about whatever that is, 366-ish grams of it in this reaction. Any questions on that method there? All right, so I'm gonna just roll through this problem one more time here and show you the ice table method in case you would like to use that, just so you can see it and see we should get the same answer. So let me just kind of copy that stuff over. We got 2 aluminums plus our iron 2 oxide there. Gonna make our aluminum oxide. And what do we got there? And we got just 2 irons there. All right, so obviously if we were going to do this approach, we would do the same thing as any other approach, which is balance the equation. We'll convert to moles. So since we already did that on the previous slide, we'll just go back over here and get our moles. So we got 4.596 moles of aluminum. And for our iron 3 oxide, 3.763. All right, so obviously those 2 steps would be just like normal. We would zero out our product side. The change part here, again, is the important part. The reactants are decreasing. So this would be minus 2x, and once again, we need that 2 for the mole-to-mole relationship. This coefficient is 1, so this would be just minus x. This coefficient is 1, which means this would be plus x. And this coefficient here is 2, which means this would be plus 2x. So again, you do have to take those coefficients into account. Otherwise, you are not really doing the stoichiometry or mole-to-mole relationship. So again, in this method, what we're going to do is just bring everybody down. And once again, we get rid of the moles so it's not so cluttered there. I'm just going to remember that it is moles, right? All right, so now that we did this, we're ready to figure out our limiting reagent. Again, to do this, we're just going to set each of these guys equal to 0. And in that case, that gives us 4.596 is equal to 2x. We're just going to divide by 2 there. And that will get us here 4.596 divided by 2 are 2.298. We'll set this guy equal to 0, which basically means we will get x is equal to 3.763. Once again, we are looking for the smallest x value. And in this case, that is the smallest. That means we don't need this number anymore. And because that's the smallest, just like we found out on the last slide there, that's the limiting reagent, and that would be the excess reagent. And again, you could do it kind of quickly. Now here again is where maybe this is beneficial. This x value here is moles, right? So that x value there is this x value, this x value, this x value, and this x value is basically all of them. So we were interested in this case with aluminum oxide. So we could very quickly go to our moles of aluminum oxide from our table equals x. So that is 2.298 moles of aluminum oxide, which means now we could just use the molar mass of aluminum oxide that we could calculate. But since we did it over here, we'll borrow it, 101.96. 101.96 grams per mole. So I'm just again going to take my 2.298 times my 101.96. That's going to give me my 234 grams of aluminum oxide. That was my theoretical yield. Now, why is this also pretty great? Because what happens, I also want to know about the other product, iron. That's not going to be too hard at this point because iron at the end equals 2 times x, which means I would take 2 times my 2.298 moles of iron. And I will end up with here 2 times 2.298 gets me 4.596 moles of iron. I could use the molar mass of iron from the periodic table, 5585 grams per mole, and times that by 5585. And within less than probably a minute, I just figured out I also made 257 grams of iron along with it. It didn't take a lot of work to do that. And the other question is how much of that excess is left over? So my leftover excess from the table is 3.763 minus x, which would be 3.763 minus my x value of 2.298 moles. And that's going to get me 3.763 minus my 2.298, 1.465. And again, that's iron 3 oxide. And again, just using our molar mass of iron 3 oxide that we would calculate, or we have kind of for us here, 159.7. 159.7 grams per mole, times that by 159.7. And again, that gets us our 234 grams of our iron 3 oxide left over, right? And pretty quickly, I pretty much could answer any question that would be asked of you through this method here. Any questions on that there? Again, as I mentioned before, I don't really care which method you use. You just have to use one that is correct. Obviously, I'll get your question. Obviously, if we put it into aluminum, we should end up with 0, right? Ish. And again, with rounding, you may not get perfect 0, but it should be pretty close to 0. Yeah.
Find out how much iron if it's smaller than
Yeah, so the way we determine it here is we first figure out really on the first calculation here how much of each of those reactants we have in moles, and that's kind of like your starting amount of each of those that you're going to toss in. Then we do this calculation here, and like I said, I chose how much iron 3 oxide to use up the aluminum. You could also do the opposite, which is how much aluminum to use up the iron 3 oxide. You could choose either one. You don't have to do both. But we do just a simple calculation between the two reactants. And this number that we get out is technically how many moles of that second reagent you need to use up the first one completely. And then what you want to do is compare that to your starting amount of that guy. And if you do have enough, that means that guy is going to be the excess reagent. The other one would be the limiting. If you compare them and you do not have enough, like say in this case, just for example, we needed like 5 moles of the iron 3 oxide, and we only have 3 to start with, basically, right? In that case, that would mean that you don't have enough, and that guy would be your limiting reagent. Other questions? All right. Obviously, the third way, as we also talked about, is just separate calculations. So in this case, you would start with 124 grams of aluminum, to convert it to moles, do the mole-mole relationship between aluminum and aluminum oxide, figure out how many grams you would produce, then do a whole separate calculation with the other reactant, the iron 3 oxide, and go from iron 3 oxide to aluminum oxide and figure out how much you would produce. And whichever one produces the smallest amount would be your limiting reagent. They all should give you the same number, whichever one you prefer. All right, let's see here. So here is that first method that we did here. All right, so let's talk a little bit about yields, which we sort of touched upon on some of these examples. And there's really 3 types of yields that we come across. One is the theoretical yield, and the theoretical yield is the amount of product that you should produce in a chemical reaction if everything went perfect, based on the equation, based on how much you're starting with. Again, like you had no side reactions, which commonly occur. You again didn't drop anything along the way, didn't lose anything along the way when you're doing the experiment. Stuff wasn't stuck on your spatula or something like that. That would be your maximum amount of product that you should produce. A yield is always a product, so that is always what you want to think about. Now, what happens in real life when you do an experiment is you're never perfect. Reactions sometimes do side reactions. Things don't completely react, perhaps, along the way. Some other things can happen. And we get what is known as the actual yield. And the actual yield is pretty much what the name implies. It is actually what you got in terms of when you did the experiment. The good news about the actual yield in problems and books is it is typically given to you. Yeah. So this is typically given to you if you were in the lab. You would find it yourself. It would be how much you produced of something, basically. Now, we then look at the percent yield, and the percent yield is the actual yield divided by the theoretical yield, and you times it by 100. For percent yield, do we want a small or a large number? We do want a large number, right? You want to yield a good amount, right? If you have a small percent yield, then that's not so great. You kind of crapped up the experiment pretty good there, right? So you definitely want a larger percent yield. You want a small percent error. Sometimes people get that confused with this thing. So percent error is different. Percent error is obviously looking at accuracy, and we do want a small percent error, but a larger percent yield. Do we want over 100%? Is that good? That's not good. Even if you try to convince your instructor, like I did 200 times the work of everybody else, that's how good my percent yield was. No, so usually if you go over 100, that usually means something maybe didn't go so well. Very commonly, a lot of times where people get kind of over 100% yield is, although we don't really do it in this class here. If you did like a precipitation reaction and you made a precipitate and it formed and you put it on like a piece of filter paper, and for example, you wanted to weigh it at the end, and if you filtered this and you were not a patient person and you didn't let your precipitate dry and you didn't maybe let your filter paper completely dry, when you go weigh it, you're going to get a lot of water weight that is really not your solid, right? But you're going to count it as your solid because you weighed it and you feel it is. And what that's going to do is bloat up your actual yield, right? And you're going to end up with more than 100%. So we don't usually want that. It's usually not great, and usually something bad happen. Now, the theoretical yield could either be given to you, but in most cases it is not. So it means that you typically have to do some type of stoichiometry problem to calculate the theoretical yield. And that could be just a basic stoichiometry problem, or it could be a limiting reagent type problem. So why don't we try one here? Yeah, I want to try this one. I'll give it a go. All right, let's say you have this reaction here. You're going to react 2.46 grams of TiCl4. The molar mass is given to you. Otherwise, you get that on the periodic table. 189.7 grams per mole. Reacts with 1.13 grams of magnesium. Calculate the theoretical yield of Ti and also the percent yield if you produce 0.542 grams of Ti. So take a few moments there, work through it. Ti is 47. I want to say 88. All right, so we have our equation here. Yep. So we are looking for the percent yield, and the percent yield is the actual divided by the theoretical times 100%. Now, in this particular case, we do have the actual given to us. So here's our actual yield, which in this case is 0.542 grams of TI. So we got the top part. Like usual in these type of problems. We do need to calculate the bottom part, which is the theoretical yield based off of the calculation. We also see that I do have grams of TiCl4 and I do have grams of magnesium, and definitely could get to moles of each of these reactants. So because I could get to moles of this guy and this guy, I automatically know that this is a limiting reagent problem, right? So somewhere along the way, you do need to determine the limiting reagent problem, and that is always the case when you have enough information for both reactants to basically get to moles. So as soon as you see that, that's the key. Like, all right, I should probably figure out the limiting reagent somewhere. All right, first step is normal. We're going to balance the equation, which it looks like it is. Second step, also straightforward. We're going to convert everybody that they gave us into moles. And again, we're not going to touch the actual yield because we're going to use that at the end. So we're looking at our reactants here. So we're going to take our 2.46 grams of TiCl4. If it was not given to us, we would have to go to the periodic table and calculate the molar mass of 189.7. But because it was, we will not. We'll just go right into the ice table. I'm going to do the ice table approach here so you can see it one more time or so. 2, 9, and I'll go 7. So that is our starting moles there. And for magnesium, 2431. Going to give us 0.04648 moles. This is going to be 0 and 0. Again, the change part here is the important part because it does take that stoichiometry into account. This is going to be minus x because that's a 1 coefficient. That's a 2. That's a minus 2x. That's a 1 coefficient. Going to be plus on the other side of the arrow because we're increasing products. And going to be plus 2x here for this guy. Any questions on that part of it there? So again, we're just going to bring everybody down. I am once again going to get rid of the moles so it doesn't get so kind of crowded there. So 0.04648 minus 2x, x, and 2x. Remember, at this point, we got to find our limiting reagent. So now we can do a pretty straightforward, simple problem. Hopefully, we're just going to set each of our reactants equal to 0 to solve for x. First one, pretty straightforward there. X is going to be 0.01297 moles. Here, that will basically give us 2x is equal to 0.04648, dividing the 2 to the other side. It's going to get us here, looks like 0.0232 moles. First off, any questions on that little calculation there? This is again just to tell us which one is the limiting reagent. We're looking again for the smallest number of moles, our X basically. And in this case, this guy is larger. So right here would be our smallest X value. And that will tell us in this reaction, it is actually the TiCl4 that's the limiting reagent. And the magnesium here is actually, I wrote magnesium twice, that's good, is the excess reagent. I'll try that one there, ER. Any questions on that there? Now, again, like I said before, once we find that X value here, that is the same X value in all these spots. So to answer the first question that we really are interested in is how much TI did we produce? So in terms of moles of TI from the table, we can see it equals X, which means in terms of moles of TI that we would produce, it would be 0.01297 moles. We then could use the molar mass of TI from the periodic table, 4788 grams per mole, to convert that into grams. The reason we want to do it in grams is our actual yield is in grams, right? So we want to make sure the units are the same, and they do need to be the same. And that will give us 0.621 grams of TI was produced. That is our theoretical yield. Any questions on that there? Now, to answer the question of percent yield, we could go percent yield is going to be our actual, which was given to us. So we're going to take our 0.542 grams divided by our theoretical that we just calculated and times it by 100%. And that will get us here 0.542 divided by 0.621 times 100, about 87.28%. Not terrible. Yield in this case. By the way, you can calculate percent yield like we did here, grams over grams. You can do it moles over moles. As long as the top guy and the bottom guy are in the same unit, you can calculate percent yield. It doesn't really matter what the unit is, but they do need to be the same. First off, any questions on that? Now, like I said before, it wasn't asked in this problem, but if we were also interested in how much of the magnesium chloride, we could get to that pretty quickly. And we could see that the magnesium chloride is 2 times X. So we would take 2 times our 0.01297, and that would get us for our other product, 0.01297, we would produce 0.02594 moles of magnesium chloride, which if we want grams, we could go to the periodic table and calculate the molar mass of it. That's 2431 for our magnesium, 2 times 3545 for our chlorine. Gives us a molar mass from the periodic table, 9521 grams per mole. And that would tell us, again, not too hard to find, that we would also produce in this case about 2.47 grams of magnesium chloride. That, by the way, would also be a theoretical yield for magnesium chloride, if you're interested. And lastly, we could also, like we did previously, if we want to know how much of that excess reagent was left over, we could do our leftover, in this case, of magnesium. And we could see at the end there is 0.04648 minus 2 times X. And that would give us 0.04648 minus 2 times our moles, or our X value, 0.01297 moles. And we will end up, in this case, 0.04648 minus 2 times 0.01297. 0.0205 moles of magnesium left over. We obviously could take that number and multiply it by the molar mass of magnesium, which we also have laying around in this problem somewhere, 2431 grams per mole. And we will see that we have left over About 0.499 grams of magnesium. In this case, we started with about 1.13 grams of magnesium. So, we used a little bit, about 0.5 or 0.6 of it. Any questions on any of those there? Again, if you use the other method, you really should get the same answer, maybe slightly different if you did a little bit of rounding, but pretty much should be the same. Any questions on that? Okay. Let's take a look maybe at a different version of that problem, different numbers. All right, let's try this one here. You react 100 grams of ammonia with 100 grams carbon dioxide. You produce 120 grams of your product there. What is the percent yield? So give that a go here. Nitrogen 1401, carbon 1201, oxygen 16. I feel like that's everybody, I think. Hydrogen 1.008. How you're progressing. So again, here we're looking for percent yield. Percent yield. So we're looking for our theoretical n times by 100%. Once again, just like the previous problem, we are given the actual yield here in the problem, which is very typical of book problems. And just like the last one, we will need to calculate the theoretical yield. In this case, just like we saw last time, we do have the grams of each reactant. So that definitely tells us we could get some moles. And since we could get the moles of each reactant, that tells us somewhere along the way we got to do it as a limiting reagent type problem. So again, that is kind of what you want to look at. They very commonly will not just straight out tell you, hey, this is a limiting reagent problem or anything like that. So those are the things that you always want to look at. And even later on, when we do it in some other contexts, limiting reagent type problems, you want to think about it. The key is, can you get the moles of each reactant? And you may have different units given to you that allows you to do that. That's what you want to look for. So again, here we have an equation that's balanced. I'm going to convert to moles. So this guy's molar mass about 1703, I think, grams per mole. This guy's molar mass from the periodic table, 4401 grams per mole. And while I'm at it, I know I'm going to need my last one there as well, so might as well just get that out of the way up front. So last guy there, we got 2 times 1401 plus 4 times 1.008 and a little 1201 and some 16 grams for our urea here. 6006 here. So just get those guys kind of up. All right, so balance. I'm gonna go initial here. We're gonna convert our moles, our grams into moles of NH3. So for NH3, we got we'll call it 5.872 moles. For our CO2, 100 divided by 4401 gets us 2.272 moles and 0 and 0. Again, the change part here is going to be minuses on the reactant side. And again, we do want to take our coefficients. So that's a 2x minus 2x. That's just a 1x basically. So minus x. That's also just an x, going to be positive or pluses on the right-hand side and plus over here for our water. That means we're going to come down here and we'll get 5.872 minus 2x, 2.272 minus x, x, and x. Any question on the table there? All right, so remember at this point, we can now just do a pretty straightforward calculation to figure out the limiting reagent. Just going to set everybody here on the reactant side equal to 0 and solve for x. That would give us, in this case, 2x is equal to 5.872. Dividing the 2 to the other side will give us an x value for this one here of looks like 2.936 moles. Saying this equal to 0 basically gets us X is equal to 2.272 moles, and pretty close, but looks like this guy is too big. So this again is our smallest number of moles. That tells us in this case the CO2 is the limiting, and our NH3 is the excess reagent. Any questions on that so far? All right, so in this case, we do need our theoretical yields, so we're going to focus on this guy, and from the table, we can see that at the end, it basically equals X. So the moles of our product here going to basically equal X, which means we already know the moles, so 2.272 moles of our urea here. And now using that molar mass we calculated up front, 60.06 grams per mole from the periodic table. That will get us here. If I use the right number, would probably be good as well, maybe. About 136.5 grams of NH2CO. That would be our theoretical yield. Now that we have the theoretical yield and we obviously have the actual given to us, we can calculate our percent yield. So we'll take our actual, which was 120. That's good as less, I suppose. 136.5 grams times 100%. And in this case, we are going to end up with a percent yield of about 87.94, we'll call it. 87.94%. Okay. Any questions on those steps? Obviously, just like previously, if you wanted all that other information, you could go back into the table with the X value and then basically solve for it. Any questions on stoichiometry, limiting reagents, percent yield, actual yield? Good. All right. We'll lay it up there for today.